Okay, having dealt with sigma notation, it's time to move on to geometric sequences. So we're out of the arithmetic series and sequence territory, and we're now moving to geometric sequences. It's very easy to remember what a geometric sequence is. It's simply a string of numbers that increases or decreases by a constant multiple. Now I've got that in red because that's where it's different from an arithmetic sequence or series. An arithmetic sequence or series, as we've seen, goes up or down by a constant number. But geometric is going up by a constant multiple. And whatever that constant multiple is, we call it the common ratio. The common ratio. And it is given by one letter, and that is the letter R. So immediately when you see the letter R, you know you're dealing with a geometric sequence or series, because that did not feature, the letter R, in our discussion of arithmetic sequences and series. Okay, so that's basically what a geometric sequence is. A string of numbers, so numbers separated by commas, for instance, that increases or decreases by a constant multiple. So here are some examples. This one is the sequence of the powers of 2, isn't it? In fact, I haven't included 2 to the power of 0, which is 1, but I could have. It's going up by 2 every time. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. That's the powers of 2 sequence. And here, this is one that's decreasing, and it's kind of the power, well it is, it's the powers of 3, starting at 81, declining by a multiple of 1/3, really. We're dividing by 3 to get to the next term. Notice that I say in the previous slide, we are talking about multiples, but if a multiple is less than 1, you are in fact dividing. I'll let you think about that at your leisure, but we still call it a multiple. Here the multiple is 1/3. Can you see, boys, that to get from there to there, I'm timesing 81 by 1/3. To get from there to there, I'm timesing 27 by 1/3. We still call that third a multiple. And the common ratio is 1/3. Okay? So, we could note that in this case, the R is achieved. We say this. Formally, it is the second term divided by the first term. Okay? The second term divided by the first term, which must equal the third term divided by the second term, which again must equal the fourth term, T4, divided by T3 of the previous term in each case. And you can go on forever. Okay? But the point is, and if that's not true, well, you don't have a geometric sequence or series. Okay? It might be arithmetic, it might be something totally different. But the fact is, it will not be a geometric sequence unless that is true. In plain English, a term divided by its previous term must equal the next term divided by its previous term. Okay? And that's how formally we calculate the common ratio. So here we can see that it's equal to 4 divided by 2. Notice I often express a fraction as a division. 4 divided by 2, which does in fact equal 8 divided by 4, which does in fact equal 16 divided by 8. Either way, you are looking at a common ratio of 2. So R equals 2. Okay?
Yep.
Very, very common. That's a handy one to know if you're in the IT world, the powers of 2. They tend to describe megabytes, bytes, kilobytes in terms of powers of 2, you may have noticed. Sorry, we've got a question. What is it?
What is the T stand for?
Term. The second term,
Okay.
read it backwards if you like, the second term divided by the first term must equal the third term divided by the second term, etc. And we're going to find that that relationship holds here, so that R equals, well, the second term divided by the first term does in fact equal the third term divided by the second term, which does equal the fourth term divided by the third term. In every case, they are equal to 1/3, so we say R equals 1/3. The common ratio is 1/3. It's going up in inverted commas, very much in inverted commas, by a multiple of 1/3 every time. Does that make sense?
Yeah.
Okay. Can we stop it there, please?